Publications that report the development of novel metal organic frameworks for a given separation application follow more or less a standard template. For example, in a recent paper, I reviewed the potential of MOF XYZ is reported for one-step purification of ethylene. The paper follows the standard template that consists of measurements of unitary isotherms at 2 or more temperatures. For example, here, the graph shows unitary isotherms for ethane and ethene at 273 Kelvin, 298 Kelvin, and 313 Kelvin. The papers then calculate the isosteric heat absorption of ethene and ethane. I'm particularly curious to note the maximum in these QST versus loading curves. I'll come back to that later and show that these maxima are really artifacts of the way in which the isotherms have been fitted. Then the next step in the template used in MOF publications is to report IAST selectivities for different mixture compositions and different temperatures. For example, here, 2 different mixture composition, 50-50 and 1:9 mixtures of C2H6 and C2H4 are reported at 2 different temperatures, 273 Kelvin and 298 Kelvin. I asked the question, why the sharp increase in the IAST selectivity at low values of pressure? Then the next step in the template used in MOF publications is to report a comparison of the developed MOF, in this case MOF XYZ, with competing MOFs with regard to selectivities, heats of absorption, or separation potentials, etc. And the final step in the template used is to report breakthrough experiments and determine the productivities. In this case, the productivity of purified ethylene is calculated from the breakthrough experiments to claim that MOF XYZ is the leading candidate, say, for one-step purification of ethylene. I have a lot of concerns and criticisms regarding various aspects of these. Firstly, I take issue with how isotherms are normally fitted and how the fits are reported. I have issue with how the QST calculations are made. I have issue with certain aspects of the IAST calculations of the selectivity. And I'd like to address all of these in this presentation. So I ask 3 separate questions. How do we fit isotherms for the unitary guest molecules in the given MOF? How do we calculate the isosteric heats of absorption? And ask the question, is the IAST selectivity dependent on the composition of the feed mixture, the total pressure, and the temperature? And indeed, what is this dependence? This presentation is really a follow-up on earlier presentations of mine on isotherm fitting procedures and QST calculations, the spreading pressure concept, and the IAST for mixture adsorption equilibrium. All of these may be viewed on my YouTube channel. I begin with a critique on how the isotherms are fitted in the publications I have examined, and explain how the isotherms should be fitted. The authors of the paper on MOF XYZ with the isotherms shown on the previous slide present dual-site Langmuir-Freundlich model fits for the isotherms, and in table S3 they provide the data for the isotherm fits for ethane and ethene at 273 and 298 Kelvin. The parameters for the exponents are unusually high. They're 2.65, 2.97, 1. They're all over the shop. It appears that the authors have used a commercial software to generate the DSLF parameter fits without actually checking whether such a parameter fits are necessary or indeed required. There's also another important fact to underline, and if you look at the saturation capacities, they are quoted to five significant digits, and they appear to be temperature dependent. Now, I don't see any particular reason why the saturation capacity should be temperature dependent. You can also see here that the saturation capacities expressed in moles per kilogram depend on the temperature, because they've fitted the individual isotherms at each individual temperature with the DSLF fits using commercial software. Another point of criticism I have is that most of the authors, in fact, indeed all the authors of papers I've examined, misquote the units of the BA and BB parameters. In this case, the authors state that the parameters, the Langmuir parameters B sub A and B sub B are kilopascal to the -1. This is completely wrong. It should be, the unit should be whatever the number, kilopascal to the minus the Freundlich exponent for that particular site. For example, if this value BA here should have the units of kilopascal to the minus 2.65969. And similarly, for ethane at 273 Kelvin, the unit for B sub B should be kilopascal to the minus 0.8846, not kilopascal to the -1. This is of importance if you want to use the parameter fits provided by the authors at using pressures with different units, say pascals or bars, and where these Freundlich exponents are important. It is quite remarkable that almost every paper I examine misrepresent the units of the BA and BB parameters. Just to drive home the particular point about the units of B sub A and B sub B, the Langmuir-Freundlich parameters, I present here the table for my own paper published in Fluid Phase Equilibrium 2025. These are the DSLF fit parameters for guest molecules CO2, methane, nitrogen, and hydrogen in all silica DDR zeolite at a temperature of 300 Kelvin. I am very particular about the units, and I quote these numbers and note that I specify that the units of B sub A is Pascal to the minus nu A, which, and in this case, nu A is 0.79. So if I use Pascal as a unit of pressure, I need to take this into account, especially when I use the parameter fit for use with different units for the pressure. So this is my particular complaint about published data where the isotherm fit parameters are not properly reported with regard to their units. I have emphasized this point in sufficient detail, so let me proceed further. Let me consider the isotherm data for ethene C2H4 at 3 different temperatures, 273 Kelvin, 298 Kelvin, and 313 Kelvin. I take that experimental data from the authors for MOF XYZ, and I try fitting with a single site Langmuir model. What I do is to plot the experimental data at the 3 different temperatures. Green squares are for 273 Kelvin, red circles are for 298 Kelvin, and the blue triangles are for 313 Kelvin. I plot the loading against the surface potential for a single site Langmuir model where the loading as a function of pressure or fugacity is a saturation capacity times B times the fugacity divided by 1 times plus BF, and the way I fit the data is to fit the entire set of data at all available temperatures using temperature dependent parameters. The parameter B is temperature dependent with a energy parameter E. Rather than plot the loadings as a function of pressure, I plot the loading as a function of the surface potential, which serves as a proxy for the spreading pressure P, and indeed the surface potential is the spreading pressure times the surface area per kilogram of material divided by R, the gas constant, divided by the temperature. At any given temperature, the surface potential can be calculated from the unary isotherm fits, where this is the expression for the surface potential, as has been explained in my videos on the spreading pressure concept and the IAST for mixture adsorption equilibrium. But the important point to note is that the loading for ethene is plotted against the surface potential for each of the 3 temperatures. All the data points lie on a unique line, and I fit the entire data set at 3 different temperatures to determine the parameters Q such, B, naught, and E. 3 parameters by fitting the entire set of data. And you can see that by the Excel solver is the one I use, where I determine the set of 3 parameters, and I determine the energy parameter to be 18.7 kilojoules per mole, the saturation capacity to be 7.1 moles per kilogram, and the parameter B naught is 5.626 10 minus 9 Pascal to the minus 1. The important point is to note that the one-site Langmuir model is of excellent accuracy for the set of data presented here, and there is absolutely no need to invoke the dual-site Langmuir-Freundlich model with exponents that vary all over the place. Indeed, the unary isotherms for C2H6 also conform to the single-site Langmuir model, and I'm able to fit the isotherms for ethane also with a single site Langmuir model. Let's turn to the calculation of the isosteric heat subabsorption of ethene and ethane. From the single site Langmuir model with temperature dependent parameter B, I can use the Clausius-Clapeyron equation for QST to establish that QST is simply equal to E. And therefore, for ethene, which be fitted with the set of parameters shown here, the isosteric heat of absorption has a constant value at 18.7 kilojoules per mole. And similarly, the one-site Langmuir fit parameters for ethane are shown here. The saturation capacity is 6.2 moles per kilogram. The value of the energy parameter E is 23.6, and this is the isosteric heat of absorption for ethane. Compare that with the QST values presented by the authors, and we now have an answer to our question that this is the maximum in the QST value, which seems a little bit odd, is a direct result of the fitting of the parameters using the DSLF fits, which are totally unnecessary. The single site Langmuir model is of good accuracy. The important message so far is that if we have isotherm data at 3 different temperatures, fit all the data simultaneously with a chosen isotherm model. If the isotherm model is not accurate enough, then you try to increase the complexity of the model in small steps. Indeed, the isotherm fitting mantra that I always use is Occam's razor, which states, do not complicate things beyond necessity. This is attributable to William of Occam, 1288 to 1347. He was an English Franciscan friar. Watch also my previous presentations where I expound on the Occam's razor philosophy. I summarize in this slide the philosophy that I adopt in choosing the isotherm model for fitting experimental data on the unary isotherms. Applying Occam's razor, I start with the simplest model, the single site Langmuir model to start with, as shown in the foregoing 2 slides for barium RPZ. Only if the single site Langmuir model is of inadequate accuracy do I proceed further to refine the model. And then I go one step up and choose the 2-site Langmuir model with 2 different sites. And this is required if there are isotherm inflections. For example, if have adsorption of say normal butane or isobutane in MFI zeolite, where the isoalkane locates preferentially at the intersections, the unary isotherms show strong inflections that can only be captured by a 2-site Langmuir model. So the next choice would be this one, and only if this fails do I proceed further to invoke the 2-site Langmuir-Freundlich model, where we have the Freundlich exponents nu A and nu B. In very special cases for isotherms of water and some alcohols in MOFs and zeolites. And for flexible MOFs, we may need to even go further and adopt the three-site Langmuir-Freundlich model. So the recommended procedure is to start with the simplest model and increase the level of complexity as demanded by the experimental data. I have argued in my publications, say, for example, this publication in ACS Omega on the reliability of the IAST, argued that the adsorption selectivity of a binary mixture is uniquely related to the surface potential that serves as a proxy for the spreading pressure. Watch also my YouTube videos on the spreading pressure concept and on the IAST. So with this background, let us calculate the selectivities for C2H6, C2H4 mixtures at a variety of pressures, compositions, and temperatures for MOF XYZ. Using my single-site Langmuir isotherm fits for ethane and ethene in MOF XYZ with parameters that are temperature dependent, I can perform calculations or to determine the C2H6, C2H4 adsorption selectivity as a function of the surface potential and the mole fraction of C2H6 in the bulk gas phase mixture for three different temperatures: 273 Kelvin, 298 Kelvin, and 313 Kelvin. The calculations are presented in the form of a 3D surface mesh that has been created using the IAST calculations. The blue mesh is at 273 Kelvin. The green colored 2D mesh is at 298 Kelvin. And the pink colored mesh is at 313 Kelvin. As I had anticipated in my previous slide, the selectivity is independent of the composition and the bulk gas phase mixture, and at any given temperature is uniquely related to the surface potential. The sharp increase in the selectivity as reported in this paper on MOF XYZ is an artifact of using DSLF fits, even though such fits are not warranted based on the data. The use of Freundlich exponents with values say 2 or 3 is totally unwarranted. The plot of the IAST selectivity should be a function of pressure, but the decrease in the selectivity with increasing pressure is due to differences in the saturation capacities between ethane and ethene. The IAST selectivity should be uniquely dependent on the surface potential for any given temperature. That's the message I want to put across here. Let's examine the experimental data for the unit isotherms for propyne and propene in ZnU2. ZnU2 is TIF6 copper TPA, and the experimental data are taken from this publication. The data for both components show isotherm inflections, and certainly for propyne, the isotherms are also rather steep, and the single site Langmuir model fails to capture the isotherms for both guest species. The dual site Langmuir model also fails, and we need to resort to the dual site Langmuir-Freundlich model. Now, what I generally do is to fit the data at the 3 different temperatures simultaneously using the Excel solver. Let's see how we do that. Let's fit the experimental data at the 3 different temperatures using the dual site Langmuir-Freundlich model. Now, the parameters BA and BB are taken to be temperature dependent, with the energy parameters EA and EB. So for each guest species, there are 8 parameters to be fitted. QA sat, BA naught, EA, nu A, QB sat, BB naught, EB, and nu B. I determine these 8 parameters simultaneously using the Excel solver. But I do not do this blindly, because I want to ensure that the parameter values are realistic. And if I use the Excel solver, I have the freedom to choose the saturation capacities such that the values are realistic. For example, for propyne, the fitted parameters are shown here. You note that the QA sat value is 6, then the QB sat value is 2.5. If you add them together, we have a saturation capacity of 8.5, which seems to be reasonable, because that is what the experimental data shows. The graph here plots the molar loading as a function of the surface potential. The surface potential is the proxy for the spreading pressure, and for the dual site Langmuir model, the analytic expression for the surface potential is derivable and is shown here. The advantage of using the surface potential as x-axis instead of the pressure is that the entire data set at 3 different temperatures collapses to a single curve for both guest species. And this is a convenient way to see if the fits are of good accuracy and representative of the experimental data. Let's look at propene. We see that saturation capacity fitted is 4.4 and 2.1. If you add them together, we have 6.5. That's about correct. So we get realistic values because we can, in using the Excel solver, we can ensure that the fitted parameter values are realistic. Note also that I have here chosen the second Freundlich exponent nu b to be unity in both cases, because perhaps only one of the Freundlich exponent needs to be different from unity. And we note also here that nu a value is 1.24 and nu a value for propene is 1.3, close together. So fitting the isotherm data with Excel ensures that we get physically realistic fit parameter values that allows safer extrapolation to lower pressures than measured experimentally in the isotherms. Such extrapolation is important for C3H4, C3H6 separations because the feed mixture may contain only 1000 ppm of propine, and we need to reduce the propine content to less than 40 ppm. A further advantage of fitting the DSLF model with temperature dependent parameters is that the isosteric heat of adsorption can be determined by analytic differentiation of the isotherm parameter fits with temperature dependent BA and BB parameters. As we shall see in the subsequent slide. From the dual site Langmuir-Freundlich fits with temperature dependent BA and BB parameters for propine and propene in ZnU2, we can determine the isosteric heat of adsorption using this expression by analytic differentiation of the DSLF model. The analytic differentiation can be carried out using Mathematica or Maple and can be easily programmed in Excel. The calculated values of the isosteric heat of adsorption for propine and propene are shown here using the fit parameters for ZnU2 as shown on the previous slide. This data has been published in this paper. Using the DSLF fits with temperature dependent parameters, I calculate the IAST selectivity for mixtures of propine and propene as a function of the surface potential and the mole fraction of propine in the bulk gas phase mixture. I do these calculations for 3 different temperatures: 278 Kelvin, 298 Kelvin, and 308 Kelvin. The IAST calculations in each case lie on a surface mesh, a 2D mesh that shows clearly that the adsorption selectivity at any given temperature is uniquely dependent on the surface potential and independent of the composition in the bulk gas phase mixture. For fitting unary isotherms, I recommend the use of Occam's razor. Do not complicate things beyond necessity. Use the simplest physical model to start with and increase the level of complexity in the isotherm model only if it is required. For example, you may need a dual site model to handle isotherm inflections, and if the isotherms are particularly stiff, as in the case of ZNU2, you need Freundlich exponents. Do not use commercial software that automatically uses the DSLF fits, even if the isotherms do not warrant it, because the extrapolation to lower pressures, it gets complicated if the exponents are not unity. Another message that emerges from this presentation is that at any given temperature, the IAST is uniquely dependent on the surface potential and is independent of the feed composition.